Welcome to the deep dive. We take complex source material, really dig in, and pull out the key insights for you. Today, we're tackling something huge, the legacy of Einstein's relativity. We're drawing a lot from Kip Thorne's work, his decades-long journey figuring this stuff out.
Yeah, it's quite the saga, 30 years or so.
Yeah,
And our goal here is, to get to the heart of what relativity predicts about these really exotic things. We're talking black holes, singularities, gravitational waves,
yeah.
even wormholes, and maybe time machines.
Oh,
But it's also about something deeper, right?
yeah.
How we know what we know in physics, what makes a theory good, and crucially, where our best theories just break down.
It's a fascinating story, and it really kicks off with just sheer audacity. Einstein basically threw out the old rule book, Newton's physics, not because of some big experiment at first, but because he wanted things simpler, more symmetrical.
That's right. Almost no experimental justification initially. So with special relativity, SR, the big thing, the absolutely foundational piece was Einstein saying the speed of light is constant, always.
No matter how fast you're moving.
Doesn't matter. Everyone measures the same speed. Which, that completely contradicts everyday intuition and centuries of physics before him.
Okay, but if light speed can't change, something else has to give, right? What breaks?
What breaks are the old ideas of absolute space and absolute time. They have to go. Einstein realized space and time must be interwoven. They have to mix.
Mix. How does that work?
Hermann Minkowski put it together really nicely later. Think about a map. Magnetic north isn't quite true north, right? It's a bit of true north and a bit of true east mixed together.
Okay.
It's similar with space and time. If we're moving relative to each other, what I see as your position in space is actually a combination of your space coordinate and your time coordinate.
Huh. So they're not separate rulers, they're just different ways of measuring on some kind of underlying fabric.
Exactly. Minkowski called it space-time, this absolute four-dimensional reality that exists whether we're measuring it or not. Space and time are just perspectives on it.
Mind-bending already. And that was just special relativity. What about general relativity?
Well, that came from what Einstein called his happiest thought. It's the principle of equivalence.
Which is?
Just the simple idea that if you're falling freely, like jumping off a diving board or floating in the space station, you don't feel gravity locally. Your weight just seems to disappear.
Right, you feel weightless.
And that realization, that gravity vanishes in free fall. That's the key.
What does it imply?
It implies gravity isn't a force in the Newtonian sense, pulling things across space. It's actually a feature of space-time itself. It's the curvature, the warping of space-time caused by mass and energy.
So we feel gravity only when we're resisting that natural curve? Like sitting here now?
Precisely. The chair pushes up on you, stopping you from following the space-time curve downwards. That push is what you feel as weight.
So the only real gravity then is the difference in the curve across space.
That's what we call tidal gravity. The stretching or squeezing you feel because, say, your feet are slightly closer to Earth than your head and feel a slightly stronger pull. That difference is the true signature of space-time curvature.
And that curvature idea, that leads directly to black holes, doesn't it? The most extreme warping imaginable.
Yeah, absolutely. And it's interesting, the idea of an object so dense light can't escape, it actually goes back way before Einstein.
Oh, really?
Yeah, 18th century.
Yeah.
John Mitchell and Laplace later, they figured using Newton's laws that if you squeeze the sun down to about 18.5 kilometers in circumference, its escape velocity would be faster than light, a dark star.
But that's different from Einstein's idea, right? Newtonian gravity is a force.
Totally different. For Newton, light particles just wouldn't be fast enough. For Einstein, it's space-time itself that's the prism. Near a black hole's event horizon, the warping is so extreme that geometry gets weird.
How weird.
Well, for starters, the radius isn't the circumference divided by 2 anymore. That basic rule of geometry breaks down completely because space is stretched so intensely.
So the distances themselves are distorted. Okay, let's say I'm watching someone, let's call him Arnold again, falling into a black hole. What do I see from a safe distance?
You see something really bizarre because of gravitational redshift. As Arnold gets closer to the horizon, the light signals he sends back to you have to climb out of this incredibly deep gravitational well.
And climbing out costs energy.
Exactly. They lose energy. And for light, losing energy means the wavelength gets longer. The light shifts towards red.
Redder and redder.
And fainter and fainter.
Yeah.
The closer he gets, the harder the climb, the more the light stretches. The wavelength increases, slowly at first, then faster and faster, doubling again.
So does he ever actually cross the horizon from my perspective?
From your perspective, no. The light gets stretched infinitely long, infinitely faint. Time near the horizon slows to a crawl relative to you. Arnold appears to slow down, freeze, and fade away right at that critical circumference forever.
Wow. Trapped on the edge, eternally redshifted into nothingness. That's quite an image.
It is. And this extreme nature leads to another amazing discovery, something from the golden age of black hole research in the 60s and 70s. It's called the no-hair theorem.
No hair. What does that mean?
It means that once a black hole forms and settles down, it's incredibly simple, utterly simple. It's defined by only three properties. That's it.
Just three. For something so complex in its making.
Just three. Its total mass, its spin, its angular momentum, and its electric charge, period.
So, what happens to everything else, like the star's magnetic field? Or if it had mountains?
Gone. Radiated away.
Mm.
That's the hair. If a star with a huge magnetic field collapses, the final black hole has no magnetic field of its own. If the star was lumpy, had a bulge,
Yeah.
the forming horizon sort of shakes off that lumpiness, sending it out as gravitational waves, ripples in space-time itself. What's left is perfectly smooth, defined only by mass, spin, and charge. Nature erases all the messy details.
Okay, so these incredibly simple, smooth objects, how inevitable are they? Do all big stars end up this way?
For stars above a certain mass, yes. The collapse is basically compulsory. Gravity just wins. It overcomes everything, trying to hold the star up.
What are the barriers it has to overcome?
Well, first, for a dying star core, there's electron degeneracy pressure. That's electrons resisting being squeezed too close together. It holds up white dwarf stars.
Right. But there's a limit to that, isn't there?
There is. The Chandrasekhar limit, around 1.4 times the mass of our sun. If the core is heavier than that, gravity crushes the electrons past their breaking point. Implosion continues.
What's the next line of defense?
Neutrons. The collapse forces electrons into protons, making neutrons. These neutrons also resist being squeezed neutron degeneracy pressure, plus the strong nuclear force itself. This holds up a neutron star.
Which are incredibly dense already.
Unbelievably dense. But even that has a limit. We think it's somewhere around maybe 2 solar masses, perhaps a bit more. It's still debated exactly where.
And if the collapsing core is heavier than that limit?
Nothing. Nothing we know of in physics can stop it. Gravity overwhelms even the nuclear force. The collapse is total, unavoidable, all the way down to, well, to a black hole.
And inside the black hole. Past the point of no return, the event horizon. What does relativity predict happens then?
It predicts the ultimate catastrophe, the singularity. A point, or maybe ring if the hole is spinning, of literally infinite density and zero volume.
Infinite.
According to classical general relativity, yes. And as you approach it, tidal forces, that stretching and squeezing effect, become infinitely strong.
So that's what gets you in the end. Not hitting a surface, but being torn apart by the curvature difference.
Exactly. For a smaller, stellar mass black hole, the tidal forces would rip you apart even before you cross the horizon. But for a supermassive one, say 10 billion times the sun's mass.
Yeah. You mentioned this earlier.
You could actually cross the horizon totally fan. You'd float in free fall, maybe for hours, feeling nothing unusual.
Right.
20 hours in that massive example.
For 20 hours.
Okay.
But then, as you get really close to the center, maybe in the last second or so, the tidal forces ramp up incredibly fast. You'd be stretched head to toe and squeezed side to side and torn into constituent atoms.
Grim. But you also said that general relativity predicts its own failure there, at the singularity. That's the critical point. Infinity in physics usually means your theory has broken down. It's screaming that you need something new. Infinite density, infinite curvature. That tells us we've hit the limits of general relativity.
So what takes over?
We think it has to be quantum gravity. The physics of the very small quantum mechanics must somehow merge with gravity. We don't have the full theory yet, but the expectation is that the singularity isn't really an infinitely sharp point.
Instead,
It's likely something called quantum foam.
Quantum foam. Okay, that sounds abstract. Can you give us a sense of what that actually means? Like, what would it be like?
It's hard to picture. Think of regular space-time as, I don't know, a smooth sheet. As you get down to incredibly tiny scales, like the Planck length or near the immense gravity of a singularity, quantum effects become dominant. Space-time itself stops being smooth. It becomes this churning, probabilistic froth. Space might not even have a definite shape or structure down there. Connections could be constantly forming and breaking. Time itself might lose its usual meaning, its forward flow. It's where space-time dissolves into probabilities.
Wow. Okay, from infinite density foam to maybe tunnels through space-time. Einstein's equations apparently allow for wormholes, too.
They do, theoretically. Solutions exist that describe these shortcuts, these tunnels connecting distant parts of the universe, or maybe even different universes.
Like in science fiction.
Exactly like in science fiction. The big problem, though, based on work by people like Kruskal back in the 60s, is that these wormholes, if they form naturally, would pinch off instantly.
Pinch off, meaning they collapse.
Yeah, faster than even light could get through. They form and slam shut almost simultaneously. So, useless for travel.
So how could you travel through one, theoretically? What's needed?
You need something to prop it open. Something to fight the tendency of space-time to collapse the tunnel's throat. And that something is, it's pretty weird stuff.
Weirder than quantum foam?
Maybe. It's called exotic material. The key property is that it has to have negative average energy density.
Negative energy density. Okay, my brain just blue screened. What does that even mean? Is it like anti-gravity stuff?
You could sort of think of it that way functionally. Normal matter and energy curve space-time inward, right? That's gravity attraction. This exotic material would need to curve space-time outward. It would actively push space-time apart, propping open the wormhole throat.
Does such a thing exist? Can we make it?
Well, we certainly don't have jars of it lying around, but theory suggests quantum effects, like squeezing vacuum fluctuations between curved plates or something, might be able to create localized regions with this property under very extreme conditions. It's highly speculative, but not ruled out by physics as we know it.
Okay, let's assume for a second we have a stable wormhole held open by this exotic stuff. You mentioned time machines. How do you get from a space tunnel to a time machine?
That's where special relativity comes back in, specifically time dilation. Remember the twin paradox. One twin travels near light speed, comes back, and has aged less than the stay-at-home twin.
Right. Time slows down for the moving twin.
Exactly. So take your stable wormhole with its two mouths, say mouth A and mouth B. Keep mouth A stationary, grab mouth B, put it on a spaceship, accelerate it to near light speed, fly it around for a while, and bring it back near mouth A.
Okay, so mouth B has experienced less time passing.
Way less time. Let's say only 12 hours passed for mouth B during its trip, but 10 years passed for the stationary mouth A and the rest of the universe.
So the mouths are now out of sync in time.
Massively out of sync. Now step into mouth A. You instantly emerge from mouth B, but mouth B is existing 10 years before mouth A. You've traveled 10 years into the past, go the other way, B to A, and you jump 10 years into the future. You built a time machine.
That seems way too easy. Doesn't that break everything? Paradoxes.
Oh yeah, big time. That's the immediate problem, like the famous Polchinski paradox.
Oh.
What if you send a billiard ball through the wormhole into the past, aimed so it knocks its younger self away, preventing it from ever entering the wormhole in the first place?
Right, the grandfather paradox, essentially. What happens?
Well, classically, physics doesn't just crash. It seems to allow multiple self-consistent solutions. Like the ball glances off itself just right so it still goes into the wormhole, but in a slightly different way. It avoids the paradox, but it breaks the idea that there's only one future.
That's deeply unsettling. Does the universe protect itself from this?
Stephen Hawking certainly thought so.
Yeah.
He proposed the chronology protection conjecture, basically an idea that the fundamental laws of physics must forbid time travel into the past on macroscopic scales.
How would that work? What stops the wormhole time machine?
The likely culprit involves those quantum vacuum fluctuations again, as you try to bring the two wormhole mouths close to that critical time difference where paradoxes become possible.
Yes.
Quantum theory suggests that virtual particles flashing in and out of existence in the vacuum would start circulating through the wormhole, going back in time, reinforcing themselves.
Creating a feedback loop.
Exactly. An infinitely growing energy surge of these vacuum fluctuations circulating through the wormhole throat. The idea is that this energy would become so intense, it would essentially destroy the wormhole, blow it apart right at the moment it tries to become a functioning time machine. Nature slams the door shut.
So the very quantum effects that might create exotic matter to hold a wormhole open could also be the thing that destroys it if you try to make it travel through time.
It seems wonderfully, or perhaps frustratingly, self-consistent, doesn't it? The physics of the very small seems to police the extreme behavior of space-time geometry. Hashtag outro.
Okay, let's try and pull this all together. We started with Einstein just deciding physics needed to be simpler, throwing out absolute space and time.
Right, which led to special relativity, then the insight that gravity is space-time curvature general relativity.
That curvature, taken to its extreme, predicted black holes, objects so simple they have no hair, just mass, spin, charge.
And inside them, General relativity predicts its own demise at the singularity, demanding a new theory,
Quantum gravity.
which we think dissolves the singularity into this probabilistic quantum foam. And that same quantum realm seems to be key for both potentially enabling wormholes via exotic matter and maybe preventing time travel paradoxes via vacuum fluctuations.
It's amazing how every theory seems to contain the seeds of its own limits. Newton leads to Einstein, Einstein's GR points towards quantum gravity.
That's the engine of progress, isn't it? Finding where our understanding breaks down. The huge challenge right now, the holy grail really, is that complete unification. Merging general relativity, our description of the universe at large scales, with quantum mechanics, the physics of the very small. We need that theory of everything, or at least a working theory of quantum gravity.
Because without it, we can't truly understand the beginning of the universe or the end state inside a black hole.
Precisely. What really happens at the singularity? What is quantum foam truly like?
And that leads to a final, really provocative thought, doesn't it? If the singularity isn't an end, but maybe this chaotic foam, could it be a beginning?
Some theories, highly speculative of course, suggest just that the immense compression inside a black hole could trigger something like another Big Bang, spawning a new universe, perhaps inaccessible to ours.
So if every black hole potentially creates a new universe from its singularity, what does that say about the singularity that created our universe in the Big Bang? Could our entire cosmos have originated from inside a black hole in some parent universe?
That's the kind of question pushing the boundaries of theoretical physics today. It connects the largest scales to the smallest, the beginning to the potential end. It's quite something to think about.
Definitely something to mull over.